This is part two of the little mini lesson on string problems and ramp problems. Okay, the part one I only had time to do the string problem. So here's the ramp. Okay, the problem goes like this. We have a safe being unloaded down a ramp from the back of a truck. Okay, and they want to set this 600-pound safe there, but they don't want it to accelerate downward. Will it accelerate downward if they just place it right there? And if it does, how much will the acceleration be? And if it does accelerate, how much upslope pushing force must be applied parallel to the ramp to prevent it from accelerating? Okay, now one of the givens in this problem is it gives you the gripping factor between the ramp and the safe, and it's called the coefficient of friction. In this case, they give us the coefficient of kinetic friction or sliding friction, which is equal to 0.3. What does that mean? So what we need to do now is get a little bit of background information first. Okay. The coefficient of friction, like I mentioned, it's a gripping factor. It basically indicates how much electromagnetic grip there is between the atoms in the ramp and the atoms of the bottom of the safe that are contacting the ramp. Okay, and there's a relationship that's very helpful. Okay, frictional force is equal to the coefficient of kinetic friction times the normal force. The normal force being that force of the ramp pushing perpendicularly upward against the safe. So that's a relationship. And if you blur your eyes, you can kind of see that this is like the word fun. So I call this the fun formula. Okay, the U of fun really being mu, the Greek letter mu. Okay, now this is in the sliding case, right? There is also a fun formula for the static friction case also. So this is for kinetic. For static, it's not equal to, but it's less than or equal to the coefficient of static friction, where it's just standing still, times the normal force. So that means that we have that the frictional force can either be equal to this or less than this. Less than being it can actually get as small as 0. So it can be anywhere. So friction can be anywhere from 0 to whatever this is right here. Okay, it's less than or equal to that. For the kinetic situation, though, the frictional force is equal to the coefficient of kinetic friction times the normal force. Okay, so that's a little background there. Okay, now let's take a look and try to get a force diagram set up. The ramp, oh, I forgot to mention, I wrote it down, but I didn't mention it. The length of the ramp is 8 feet, and the height where it meets the truck is 4 feet high. So we have 4 feet high, 8 feet long. We can figure out an angle from those ramp dimensions. So this is 4, and this is 8. Can we find out this angle? We sure can, can't we? Okay, opposite over hypotenuse is the sine, right? So the sine of that angle is equal to the opposite side, which is 4, over the hypotenuse, which is 8. Okay, so therefore we can find the angle whose sine is 4/8, or 1/2. And we know what that is, right? That's equal to 30 degrees, or if you didn't, you could plug it into the calculator. So this angle here is a 30-degree angle for the angle of elevation of the ramp. That's going to be very helpful for us. Okay? Now that's not a force diagram, that's just getting us our angle. These aren't forces, these are lengths here. But now we need to draw a force diagram using the safe as our point object. And we're not going to worry about the height of the safe, because if we did that, then we'd have to deal with torques and so forth, which we haven't gotten to yet. Okay, so let's just treat that safe as a point object. I will draw that right here. Draw it right here, maybe. There's the safe, that dot. Okay, and what kind of forces are acting on the safe? Well, there's the Earth pulling down on it with a force of 600 pounds. The force of gravity, right? Its weight. And then we also have the normal force. Let me draw the angle of the ramp there. There's 30 degrees. Okay, we have the normal force, which is perpendicular to the ramp. So I'll draw that perpendicular. And I'll label that N. And then we also have the force of friction, don't we? Because it gave us that there is a coefficient of kinetic friction of 0.3. And remember, the frictional force is equal to that coefficient of kinetic friction times the normal force. So which way is friction pointing? Well, the tendency of the safe would be to slide downward, wouldn't it? So we can make a pretty good guess that the frictional force must be pointing upslope, parallel to the ramp. And it's going to be a certain length. I'll just guesstimate it to be that long there, and I'll label that F for friction. Okay? I go, okay, what if we divide this up here, make it along the horizontal line there, and we put all our angles relative to that? That wouldn't be too smart about it, because we'd end up with two angles. One for the frictional force angling up above the positive x-axis, and one for the normal force. Why don't we be a little bit more clever and tilt our head? We'll use the old head tilt method and treat this as our positive x-axis, and this is our negative x-axis, and treat this as our positive y-axis there and our negative y-axis there. So we're just translating the x and y-axis to minimize the number of angles that we have to deal with. Okay, sound fair enough? Okay, so now since we have that, we can see that these are along the x and y axis, so we don't have to mess with any angles. This one here, though, the 600-pound force, that's the one we have to break up into components. Now, this is the force. The components are always the shorter legs of the right triangle, right? The vector triangle. So this is one component, and this is the other component. The components are always the shorter legs. The force is the longer, the hypotenuse. Okay? That's something that people, people are just starting out, they oftentimes make mistakes. Okay, so what is this angle here? Well, this angle here is the same as this angle here. Okay? We can see this is 90 degrees. This is 30, 90, that'd be 60 here. This is 90 degrees. Okay, 60 from 90 gives you 30. So that's a 30-degree angle there. Good, so now we have that. This is the side adjacent to that angle, so we'd use cosine. So this is 600 cosine 30, which, if you multiply that out, it comes out to be 519.6. I'll just circle that. And then this component opposite to that angle would be 600, the length of the hypotenuse vector, times sine 30. Sine 30 is just a half, so half of 600 is 300. Okay, so 519 pounds there, 300 pounds there for that 600 pound vector that's broken up into components. Okay, so far so good. So now remember, the safe can only go in the direction of the incline. It's not going to fall through. It's not going to jump up. It's not going to jump out like that. It's going to probably go down like that if it moves at all. All right, so really then, now we can, let's find what F is. Remember, fun formula. F is equal to the coefficient of kinetic friction times the normal force. Okay. All right, so let's substitute in. So F would be equal to 0.3, which is the coefficient of friction, times that normal force. So far so good, but we don't know what N is yet, except for the fact that we can use our sum of the forces idea to figure it out. Okay, so let's look at that. Let's look at our force diagram. We see that N pointing up must be equal and opposite to the downward component here, 519.6. So we can say the sum of the forces in the y direction, y being, along this axis, is equal to, it must be equal to 0. If we let up be positive, that'd be N. If we let the downward direction be negative, that'd be plus a negative or minus 519.6. They have to add up to 0. So therefore N equals 519.6 pounds. Now we can go ahead and substitute that in right up here. So F then, so we're subbing that in, F then would be equal to 0.3 times the 519.6 pounds, okay, which is equal to 155.9 pounds. So that's the force of friction. Okay, that's the force of friction. Now, that force of friction, if we look at, that's equal to 155.9 pounds. But look at the downward component, the component going parallel downward. That's 300 pounds, which is bigger. Well, let's take a look. So use the sum of the forces in the x direction. Let's set them equal to 0 for now, assuming that it's not going to accelerate. And what would we have? We have the upward component, 155. That's 155.9 pounds. We'll call that positive, and then this pointing downward would be negative. So we have 155.9 plus a negative or minus 300 equals 0. Does it equal 0? Well, add 300 to both sides. We get 155.9 equals 300. Ouch! That can't be, can it? So, it is going to accelerate, isn't it? By how much? Well, let's modify our approach here. Instead of setting it equal to 0, which is not true, we'll set the sum of the forces in the x direction equal to ma. Okay? ma. Alright, but we don't know the mass, do we? Okay. But we know that the sum of the forces are, we know that that's 155.9 minus 300 in the direction parallel to the downward, parallel to the ramp, which is equal to what? Let's see. That's equal to negative 144 approximate 0.1. And that's equal to MA. All right. Well, that may be equal to MA, but what's M? We're working in pounds, which is not in the international system. How can we figure out the mass of a 600-pound object on Earth? Okay, well, we can use good old weight equals MA, or acceleration due to gravity in this case, which would be G, right? So if the weight is 600 pounds, that's a unit of weight. We can find the mass if we know what the acceleration of gravity is in the English system, and that happens to be 32 feet per second squared. Now we can solve for M. M would be equal to 600 pounds over 32 feet per second squared, which would be 18.75 units of mass. Okay, now what would be the English system unit for mass? It's called the slug. So 18.75 slugs. That's the English unit for mass, whereas the international unit for mass would be kilogram. The international unit for force would be the Newton. Here we have the English unit of mass, which is the slug, whereas the unit of force in the English system is the pound. Okay, so we have 18.75 slugs. So now we can go ahead and substitute that in right over here for mass. So we have negative 144.1 equals 18.75 slugs times A. Rearrange and solve for A. Pesky light again. That's equal to negative 144.1 over 18.75. And that gives us 7.68, negative 7.68 feet per second, or per second squared. 7.68 feet per second. That's the acceleration if there's no force pushing up to help the friction force do its thing. Okay. So now the next question is, how much upslope pushing force must be applied to prevent the acceleration? Well, that's not too bad of a problem. We can get back to our idea. I'll just do that in red here. Remember, it wasn't true before that the sum of the force is equal to 0, but if we want the sum of the force to be equal to 0 in the x direction, we have our 155.9 frictional force pointing upslope. We have our downward component, 300-pound downward component parallel to the ramp due to the weight of the safe. And we have to add one more force here. I'll just call it F sub P for pushing force. All three of those have to add up to 0. Now we can find that. Okay, we already found that this was equal to negative 144.1. So negative 144.1 plus our pushing force have to add up to 0. So therefore, the pushing force must be equal to 144.1 pounds pointing up the ramp, directed upslope. Okay, so in summary then, if we don't add any pushing force, that safe will accelerate down the ramp at a negative 7.68 feet per second squared. However, if we want to prevent that from happening, we would have to provide an additional pushing force directed upslope of 144.1 pounds. Thanks, guys.